All right, welcome. In this video, we're going to be analyzing graphs of polynomials, and this is going to be the third lesson in Unit 6 in Algebra 2. So the last couple lessons were like, how do we produce the graph of a polynomial? And today, the discussion is going to be more like, okay, what are we going to do after we've got a graph of a polynomial? Like, what can we say about the function based on its graph? So I'm going to start you off with kind of like, let's sketch the graph of a parabola on a limited domain. So I'm just going to sketch in the graph of y equals x minus 2 squared on the domain. All right, there we go. It's not great enough. Definitely good enough to get the point. So what happens to the graph as x increases? And now this is kind of a leading question that what your answer for this might be my answer for the next kind of question. But I'm seeing as x increases, I'm seeing the graph, it's going down and then up, right? It's going down and then up as x gets bigger. Also, I'm just going to write this in while I say this. If you ever graph functions on like a TI-84 or some kind of graphing calculator, at least an 84, I'm not sure about other types. When it traces out the function in the graphing window, it does move left to right, like you're drawing or writing, okay, at least in English. And so I would say it goes down, then up. And it's like, okay, well, what happens to the value of y as x increases? Well, I could say the same thing about that. It goes down and then it goes up. But I think better language for that might be to say that y decreases until it hits 0 and then it increases. Okay. And at x equals 2, I think we've already talked a little bit about, especially with the parabola, how x equals 2 is what we might call a minimum on the graph of y equals x minus 2 squared. But specifically what I'm trying to point out here is that the graph changes from decreasing to increasing. Okay. But that was probably not the best nomenclature grade, because how can a graph decrease or increase? And more graph, less graph. The y coordinate is decreasing than increasing. So function changes from decreasing to increasing. I don't know. Okay, but I hadn't really defined what I meant by a function increasing yet, so let's just do that right now. So I'm going to say that a function f of x is what we would call increasing if an increase in the input x causes an increase in the output f of x. I think that's going to be the simplest definition for us to take in this class, but let me just draw you a picture of a function that's increasing. Okay, as x increases, the output increases. Okay, it's going up. That's probably going to be what you think of when you think of increasing. Okay? As I move left to right, the graph goes up. Okay? And if a function is decreasing, well, it's going to go down right there. But I've got a little bit more to say. That didn't go well. I've got a little bit more to say about this. So let's investigate like the graph of an actual polynomial. All right, so here you see I produced a professional level graph of y equals x minus 2 squared. Okay? But the point I want to make is that if you're working with a polynomial, I've said this before, that polynomials are both continuous and smooth. And what I mean by smooth is that if you just keep zooming in on this polynomial, if like look, eventually it looks like, wait a second, that's not even a curve, that's a line. Okay? And so a different definition that some people might take of increasing or decreasing is the slope of that line. You see that, okay, it looks like a line and the slope looks negative. Okay, and if the slope of the tangent line is negative, then the function is decreasing. That's probably the definition we're going to take when you're in my AP Calculus class. But for now, I actually think that it would be best for us to think about as x increases, y increases is going to be our definition of increasing. Okay, so over here on the left half of the parabola, where it was where the function was decreasing, okay, we saw that negative slope. But if I zoom back out, we see, okay, we've got some curvature. And if I zoom in over here, where it's increasing, all of a sudden, this looks like, you can't really see it, but that's a line with positive slope. That's just something I want to throw out there. So just to recap, increasing is as I move left to right, the graph goes up. Decreasing is as I move left to right, the graph goes down. All right, now let's talk about a maximum and a minimum. Okay, so a local maximum, which a lot of people also call a relative maximum. So I just need you to be aware that local maximum and relative maximum are exactly the same thing. Maybe we're going to say it's at a function's at a maximum if it changes from increasing to decreasing at that point. So I'm just going to kind of type it or write in that other name. And so let me just draw you a quick example of what that might look like. Okay, a function that's increasing is going up like that, and then all of a sudden it decided to decrease. Okay, that's the maximum. Okay? And on a polynomial, it's always going to be like a smooth hilltop, but that's not always true in general. Okay, I might talk about a local minimum, and one function that has a local minimum that's not smooth is going to be y equals the absolute value of x, right? That looks like a v, and it's got that bottom of the v at x equals 0, and if we think about it as we move left to right, that is a place where the function changes from decreasing to increasing. Okay? We could also call this a relative minimum, right? Say that as well. Okay, but a relative minimum in general doesn't have to be a sharp corner, right? Think about the graph of y equals x squared, right? That's very smooth at the bottom of the parabola, and that's definitely a relative minimum, because as I move left to right, at that point, at the vertex of the parabola, the function has changed from decreasing to increasing. So that's all we're looking for maximum and minimum in this class. Okay, now that's all of the new facts I've got to tell you about today. At this point, I'm going to just start working in on some examples and really practicing the skills that we're trying to build in this unit, which is like, sketching graphs, factoring, and then folding in this new stuff that we just learned about, increasing, decreasing, maximum, minimum. So we're going to start by sketching the graph of g of x equals x squared minus 1 squared in the space below. Okay, so x squared minus 1 is the difference of two squares. So I'm going to need to factor this thing a little bit more before I'm ready to sketch. Okay, so I factored it. And then I also distributed the exponent, because I was squaring x plus 1 times x minus 1, meaning I would have 2 copies of x plus 1 and 2 copies of x minus 1 as well. Okay, so I've got 2 of these. So that's telling me that I'm going to have a double root at x equals negative 1 and another double root at x equals positive 1. And so, last time we learned that a double root corresponds to a bounce on the graph of the polynomial. So we'll see all that when we go to sketch. First, I need to think about the degree and the leading coefficient of this polynomial. Oh, okay, so we're good. So the degree here is going to be 4, right? Because if I squared x plus 1, I'd have x squared plus some other stuff. And if I squared x minus 1, I'd again have x squared plus some other stuff. And then if I multiply those together, I would have x squared times x squared, which is x to the 4th, plus a bunch of other stuff. Okay, so this is going to be degree 4. The leading coefficient is going to be 1 because, well, what else could it be? But just copy that in. But definitely positive. Okay, we're not seeing any negative number hanging out on the outside. We're not seeing any, like 1 minus x or anything on the inside of parentheses. It's going to be a positive leading coefficient. So, knowing that, even degree positive leading coefficient is going to look, at least in some way, like the graph of y equals x squared on the outsides. The in behavior on both sides is going to go up. So I think we're ready to sketch the graph of this thing, because we know that there's a double root at x equals negative 1 and a double root at x equals positive 1. Oh, it's pretty much off my shot. Oh, but then this is 2. That's a shame. Okay, hopefully that works. Yeah, that's good. Okay, and so the graph comes from above. Respect that in behavior, but then it's got to bounce at x equals negative 1. And then it's going to come up, and it's going to bounce again at x equals positive 1. And then it has to go up from there, but that does fit with our in behavior, so that kind of makes sense. Okay, that's going to be my sketch. Okay, so at what values of x does g have a local minimum? Okay, we can see where the minima are occurring. It's at those zeros right here. There's 1, there's 1, right? Okay. So I'm just going to say at x equals negative 1 and x equals 1. But you can't just say there's going to be a local minimum there because you see it's a double root. It could also be a local maximum. Right? Now, I'll tell you it's going to be one of the two if it's a double root. But, this graph could be upside down. I could just multiply this whole thing by negative 1. I'd still have double roots, but they'd be relative maximum. That's a different discussion. All right, at what values of x does g appear maximum? Okay, well, I'm seeing a local maximum right here. Okay, so I mean, it looks like it should be halfway between -1 and 1. And in reality, it is. It is at x equals 0. But we don't really have the tools to determine that for certain. Okay. I mean, now, I actually think that, if you're really up with it in this course and you really understand what's going on, I think you could understand why the maximum has to occur at 0 because of the symmetry of the function. How if I go all the way back to like the original statement of the function, if I go and I plug in a negative number for x, I'm going to get the exact same result as I would get if I plugged in a positive number. So these numbers between, say, 0 and 1, whatever's happening there, it's reflected on the other side between x equals 0 and x equals -1. And if you kept thinking about it, you would realize that they were both increasing, pardon me, not both increasing. It had to stay positive the whole time. And the same thing had to happen on both sides of the y-axis. Therefore, the maximum had to happen at the y-axis. So probably not. I'm going to say no needs calculus. Okay, that's one of the big things that you would study in a calculus class is how to determine the locations of a maximum or a minimum, which is a really big deal in actual applied context because there's all sorts of situations where we're trying to maximize things, like profit or I don't know what else. Profit just comes to mind, and I know of things that we want to minimize, like risk of injury or death or something. There's all sorts of things we might want to minimize, and so that's a very common, optimization is a common problem, a common use of algebraic math. So, yeah, I think that's enough about that. What values of x is g increasing? Well, someplace where as I go left to right, the graph is going up. So I think I might use red for that. And I'm seeing us going up there and also up there. So that's going to be between -1 and, if you believe me, 0. Okay, so from -1 up to 0, but also from 1 to infinity, so where x is greater than 1. Okay. G will be decreasing pretty much everywhere where it's not increasing, but I'm just going to draw these arrows here. And we see the graph going down as I move left to right. So the G is going to be decreasing when x is less than -1, or also when x is between 0 and 1. And in this case, I wrote these as inequalities, but if you want to write these in interval notation, be my guest. You're more than welcome to do that. All right, let's work another example. Okay. Here is a picture of a graph of a polynomial. This is going to be common for us in this class, right? Since we don't have all of these techniques that you need to solve for intervals on which a function's increasing or decreasing, or solve for maximum or minimum, we're kind of just going to look at a picture and make these decisions. So the degree of p, assuming that nothing weird is happening outside of the window we can see, I might just attach some arrows there, looks like an odd degree polynomial with a positive leading coefficient because of the end behavior. Now, I'm going to say that the degree of p is at least 3. In reality, it's probably just 3. Okay. Actually, maybe I'll say probably 3. Definitely odd. Okay. Is the leading coefficient of p positive or negative? I'm going to say it's positive because of the end behavior. As x goes to infinity, y is going to positive infinity as well. And then as x goes to negative infinity, y is also going down to negative infinity. So, that's the hallmark of an odd degree polynomial with a positive leading coefficient. Okay, on what intervals is p increasing? Well, let's see. Increasing is where, as I move left to right, the graph is going up. So definitely when x is bigger than 1. But maybe I'll do this with interval notation. 1 to infinity, also before -1. So negative infinity to -1. On what intervals is p decreasing? Well, that would be over here where it's not increasing between -1 and 1. Where does p have a relative maximum? Okay, that's going to be right here at x equals -1. F's going to have a relative minimum right here. That's going to be at x equals +1. And then now we're going to be asked to compute the leading coefficient of p, and I think that's going to require a little more room. All right, so this is a problem that we solved a little bit in a previous lesson. You know, like, hey, here's a picture of the graph, write me an equation for it. But now that we know about double roots and stuff, I think we can, answer this question and make it a little more interesting. So I know we were going to write down like the factored form, the skeleton of the equation. So y equals some number, some leading coefficient that I'm hoping to find eventually, times, well, I see a 0 here at x equals -2, and that feels like a single root because it's passing through confidently. So x minus -2 to the first power. And then I see another 0 over here at x equals 1, which is a double root. I guess I can see that because of the bounce. Now, I don't necessarily know, I guess, that it's not a quadruple root, but I'm pretty sure it's not. So x minus 1 squared. Okay? And so really, I've only got one piece of information that I haven't used yet, and that's this y-intercept. So I'm going to say, hey, that's the point where x is 0, and y is equal to 1. And we'll use that to solve for a. So that's going to be 1 equaling a times 0 plus 2. It's plugging in 0 for x, 0 minus 1 squared. Okay, if I square -1, I'm going to get +1. So a times 2 equals 1. That means a needs to be a half. And that's going to be the leading coefficient of p. Okay, yeah, there you go. All right, let's work another example. So, I don't know what happened here. All crunched up. Is the graph of y equals -2x times x plus 3 squared times x minus 4 increasing or decreasing at x equals 4? And justify your answer. Okay, so what we're going to do to answer this question is we're going to start by sketching the graph. Okay, and then hopefully our sketch should make it obvious to us whether the function's increasing or decreasing at that particular coordinate. So, first I need to think about the degree of this polynomial. I'm seeing 1 power of x, 2 more here, so that's a total of 3, and then a 4th power, so that's degree 4. Okay, the leading coefficient is going to be negative because of that -2 right there. Okay, and so a degree 4 polynomial with a negative leading coefficient, even degree, negative leading coefficient, it's going to go down on both sides. Think about the end behavior. Okay, and then I'm going to write out the zeros. Okay, I've got -2x could equal 0 when x was 0. So I've got x equals 0. That's going to be a single root because there's no other exponent on the x. X equals -3 would be a 0 because that would make x plus 3 equal to 0. That's going to be a double root. Throw that out there. Okay. And then x equals 4 is also going to be a root. That's going to be a single root, right? Because I don't see any exponent on that x minus 4 there. Okay, so I'm going to go in. I'm going to sketch myself an x-axis. I'm going to label my zeros. That'd be -3, 0, and 4. All right. Think about the end behavior, start from there. Okay, go up. -3 is the double root, so I need to stick it down. And then the other two are single roots, so, oh man, it's gonna need to turn around a little quicker. And pass through at x equals 0 with confidence, and then passing through at x equals 4 with confidence as well, because these are single roots, right? Not hesitating before they go through like they would if it was a triple root. Okay, so that's going to be a sketch. Now, at x equals 4, oh look, like it's in the midst of going down through the x-axis. So I'm going to say this function is decreasing. And then the reason, let's see. Because y is going from positive to negative at x equals 4. Okay, and that would be my reason. All right, I think one more example for us to do would be, hey, here's a function given to you algebraically. Does it have a maximum, a minimum, or a neither at x equals 1? Justify your answer. Okay, so I'm going to do the same thing I did in the previous example. I'm going to produce a sketch of this function. And then I'm going to use that sketch of the graph to determine what's happening at x equals 1 in this case. So let's get to it. So first things first, let's determine the degree of this polynomial. Okay, I've got 3 powers of x here and 2 powers over there, so that'll be in total 5 powers of x. Okay, the leading coefficient is going to be 1/3 because if I multiplied x plus 1 out 3 times and x minus 1 out twice, and then multiplied those products, I'd end up with, just 1x to the 5th. And then if I distributed it in the 1/3, I know that would be the leading coefficient. It's 1/3, which is positive. And what matters about this is it's odd. Okay, so if I've got an odd degree polynomial with a positive leading coefficient, it's going to kind of look like that, where as x approaches positive infinity, y approaches positive infinity. As x approaches negative infinity, y will also approach negative infinity, much like the graph of y equals x cubed or y equals x. Okay, so I'm going to now, I'm going to list out my zeros. X equals -1 for this one, right? Because if x was -1, that factor would be 0. That's going to be a triple root because of that exponent of 3. And then x equals +1, that's going to be a double root because of that exponent of 2 right there. Right, and then over here, whoops, that's too much x's. Yeah, perfect. So 1 and -1 are my 2 roots. And odd degree polynomial with a positive leading coefficient means I need to come from below. So it's like down here. X equals -1 is a triple root, so it's got to like slide through hesitantly. It's really got to go through and it's almost flat. It really is flat as it's passing through. But you know what? I could do better. Oh, pardon me. I just feel like I could draw a better sketch. So I'm going to try to do that. Okay, yeah, better. And that one's actually maybe even worse, but it's all right. I'm not going to draw it again. And at x equals 1, I'm going to have a bounce because of the double root. Okay. So when it's asking, do I have a local maximum, a local minimum, or a neither at x equals 1, I'm just going to say right here, that is a relative minimum that I've just hit with yellow highlighter, right? It's bottomed out. So what I'm going to say is that this is a relative minimum. And here you could probably say because the graph of f went from decreasing to increasing, or that f went from positive to 0 back to positive as it went through x equals 1. Either way. But really the biggest of pictures, I think we will worry about justifying our answers a lot next year in pre-calculus and the year after in calculus, and not so much in the Algebra 2 course. I think that's going to be all for this video. Thanks for watching.